Hello, so we're just going to be walking through the midterm problems for spring 2019. So the first problem we see, we're going to be doing some Python print. So we see here we are given some code, and we're going to see what happens when we run the next few lines. So the first line we have is z divided by y, or in other words, 1 divided by 2, which is 0.5. And then we have a divided by y, which is the string CS88 divided by 2, which really you can't exactly divide strings with ints and numbers, so this is going to error. And next, we see this syntax. So if this looks kind of familiar, it might be because we did like maybe a list comprehension stuff. So if z 4 divided by y, else x for z in list. Like this is what the list comprehension might look like, if you remember this from maybe a lab or something. But it's the same. It acts the same way as it would in a list comprehension. So we're going to be returning z if this is kind of a truthy value, and if it's not, then we're just going to return x. So we'll see that what does z 4 divided by y give? It's 1 4 divided by 2, which gives 0, which is a falsy value, so we're just going to return x. And x, in our case, is 3. So now we're going to do a times 2, which is a string multiplied by 2. So we can multiply strings, actually, because it just gives us kind of just like repeats the string twice. So we get CS88, CS88. Cool. Now when we do a or x, we're kind of, remember that or statements kind of short circuit at the second that they see a truthy value and they return it, or else they return the last falsy value they see. So we see that a is a string CS88, and we know it's not null string, so we immediately hit our first truthy value, so we just return CS88 here. Next, we're doing print moves23. So moves23 is up here. So we see in moves23 we're given an m and an n. So in our case, it's going to be a 2 and a 3. So now we're going to do if m times n, which is 6, is greater than 9, which is not. So we're going to go to the else. So now we're just going to return none. Next, we're going to do moves32. It's kind of just the same thing flipped. So it's going to return none. But the reason why we don't see none again out here is because before we printed the none here that was in here, we printed it so it shows up here. But since we don't have a print statement around this moves, we're not going to show the none. Next, when we do moves 4-3, it's going to be if 4 times 3 is greater than 9, which is 12, which it is, I'm going to return m. So m in this case, let me see. The m in this case is going to be 4. So we're just going to be returning a 4, and there's no none above it. Next, we're going to do move 7-7. 49 is greater than 9, so we're going to be returning a 7. And then when we do this, it's going to be moves 3-3, which is 9, which is not greater than 9. So this is going to be a none, and this I know is going to be a 4. So none plus 4 doesn't really make sense, so we're going to get an error here. Then when we do moves 5-5, we're going to, remember we also, again, this or, the first time we hit a truthy value, we're going to return it. So moves 5-5 gives us 25, which is greater than 9, so we're returning 5 here. And we hit our first truthy value, so we just return 5 here. Cool. So now we're going to do funhof, combine, and a. So up here, let me copy this here so it's easier to see. So I'm going to be doing funhof, takes in some function, and this function is going to be applied to x and x for x on the list if this gives me a truthy value. Cool. So I see in my case that my function is going to be combine. And so combine just returns a plus b if a plus b is a truthy value, or else I'm going to return combined. So in here, I'm going to be doing, all right, so now I want to figure out what my list is, right? So my list in this case is an A, and you might think it's weird that we're passing in a string as our list, but we can kind of think of strings in the same ways as we do lists, because we can still index into a string and get, like, let's say, like the first letter or something, right? So in our case, we're going to be going letter by letter. So this, for X in list, this is going to go letter by letter through CS88, and then we're going to check if those two letters combined give a falsy value. If not, we'll actually combine them. So we'll see that, let's go through just like one loop, just to try to understand what happens. So in the first loop, loop 1, X is going to be equal to C, the character C. So now we're going to check f of xx. And f of xx gives us combine C and C. And so if C plus C is true, which it is, it gives us C, C, and it's not a falsy value. We're going to just return CC. So this goes to CC. Cool. Now in loop 2, our x is going to be equal to s, the character s. Our f of x is going to be equal to ss this time, and which is truthy, which we're going to return it. And so if we just follow this pattern, this eventually just becomes, I can see that I'm going to have a list that's like repeating each character. So I'm going to have CC, I'm going to have SS like we already did. I'm going to have 88, and I'm going to have another 88. Right, so this is going to be my final answer. Just put it down here. Cool. So now we're doing the same thing except with an actual list this time in the next problem. Right, so let's go back up here. Let's delete this. So now we're going to have 0, 1, 2, 3 as our list. 0, 1, 2, 3. And everything else is going to be the same. We're just going to use the same combine function. So let's just walk through a few loops again. So loop 1, we'll see our x is going to be equal to 0, right? And then our f of 0, 0 is going to be, a plus b is going to be 0, so that's a falsy value. So I'm going to be returning combined instead. So when I return combined, this first f of x, when x is equal to 0, is going to be this kind of string combined. So the first part of this list is combined. All right, and then just keep looping through this. So on loop 2, x is going to be 1, and then f of 1, 1 is going to be 2. 2 is a truthy value, so I'm not going to be returning combined. And so the next item in our loop is just going to be a 2. 2. And we'll just do one more loop to see, kind of try to see if we can see a pattern happening. So in this next loop, x is going to be equal to 2. F of 2, 2 is going to be equal to 4. 4 is truthy. I'm not going to return combined. And so I can just write a 4 in here too. So I'm realizing that I'm just going to be doubling everything, and 3 is going to be double 2. So I'm just going to be giving a 6. Cool. So now I'm going to be doing this next problem. So we're going to be doing the same thing, except our list is -2, -1, 0, and our function is moves instead, not combined. So if you come back up here so we can see the functions well. So our list is -2, -1, 0. And we're going to have a function moves, just remember that. So we're still going to be doing this fun hof, right? So we're going to be doing, iterating through the list and checking if moves of xx make sense. So in this first one, let's just go through some loops again. So loop 1, x is going to be equal to -2. And then we're going to do moves of -2, -2. And so we're going to see 4 is not greater than 9, so we're going to return none. And so we see that this is going to be none. So if this moves function returns none, that means we know that this function returns none. So that means we're not going to include it in our list because we're only going to include it if this is evaluates to true. Right, so then in our next loop, x is going to be -1, and moves of -1, -1 is also going to be none because we know that 1 times 1, -1 times -1 is not greater than 9. So we're going to be returning none again. And again, we don't include it. And then we know for 0, we're definitely not going to include 0 because 0 times 0 can't be greater than 9 either. So essentially, we're just going to get an empty list from this. From here, we're going to get an empty list. Right, so if we come down here, we know this is going to return us an empty list. But I see this and here, and I see that I know that ands are going to short circuit the second I see a falsy value or return the last truth value. So I don't even need to evaluate this, and I know that my and statement is just going to give me an empty list because an empty list evaluates the falsy. Okay, well, moving on, we're going to be doing grades 100, and here we have grades defined. So let's say I was like a Python interpreter, and I was stepping through this code. So I'm going to hit this line, right, and I'm going to say grades 100. So now I'm going to go look for some variable called grades. And then I'm going to look above, I'm going to look up here, and I'm going to look for some grades. Maybe probably a function because I see circular brackets, right? But I don't see a grades up here, and I see a grades is, I know that there's a grades down here just because like I see it, but Python doesn't know what's beyond this line, right? So this is actually going to error because Python's not going to be able to find anything called grades, and it's not going to be able to call a function on nothing. Cool. And for the last problem, we're going to be going through this new function getElement. So get5 equals getElement 5. So when we do call getElement 5, k is going to be 5. We're going to define this list here. And we're not going to go into the list because we haven't kind of called that. Sorry, we're not going to go into that function because we haven't called the function, and we're just going to return that f. So this becomes f. Now we're going to do get5 on this list 1, 2, 3, 4, 5. So essentially we can think of get5 as f calling out 1, 2, 3, 4, 5. Right. So now we're going to go into this function now actually, and we see that our list is going to be 1, 2, 3, 4, 5. If k, which we know is our 5, is less than the length of the list, and the length of the list we have here is 5. So 5 is not less than 5, right? So we're just going to be printing, let me see. And we're not going to put quotes around this because when we print, remember we don't have quotes around our strings. And we only have quotes around it when we return strings. And so next we're going to do get5 of range 1 through 10. Remember that the 1 is inclusive and the 10 is exclusive. So it's going to look like some function call like this to all the way to 9. 10 is exclusive, right? But the length of this is still 10. The length of 10 is still great. Oh, sorry, actually, length of 9, but that doesn't really matter because 9 is still greater than 5. So we're going to return list k. So we're going to go to the kth element. So this one's a 0, this one's a 1, so 3, 4, 5, 1, 2, 3, 4, 6. Right, so 6 is going to be our 5th element, and so we're going to return the 6, and then we see that there's this print line here, right? But since we return, we don't do any. We immediately exit our function, our frame, and so we don't do anything below the print line or the return line. So we're not going to have a print statement below that 6. Well, this next problem is going to be an environment diagram problem. So we see that our code is right here, and so we can get started with our environment diagram on the left. So we see that boba is going to be assigned for us, and then dessert's going to be assigned for us. Milk tea, we see here, is going to be assigned to 10, so we're going to write a 10 here. And taro tea is going to be assigned to whatever the return value of dessert boba is. right? So we see that we've been open a frame for dessert here, and we know I'll draw a small arrow to taro t, because I know whatever I return from this frame is going to be put right here, right? So now in our dessert frame, the first thing I'm going to do is assign my variables. So I see in dessert, I need to assign a shop as my argument, and I'm passing in boba. And boba is going to be this kind of pointer. So I'm going to copy that in. I'm going to copy a pointer, and I'm going to be pointing it to this function. So now I'm going to be assigning a boba function inside here, because I'm on this line. I see that I'm defining a function, and its parent is f1. So now after I've done that, I'm going to return. So I'm not going to go into boba, right, because I haven't called it yet, and I'm just going to be returning that boba function. So I know that, again, I have this arrow here, so whatever I'm going to return in f1, I'm going to be copying that. So I'm copying the pointer over, and I'm erasing the pointer so it's easier to grade for the TAs. Next, we're going to do price. Oh, sorry. Yeah, so now we're going to do price. So now price, we're going to have to be calling taro t and then 50. So we're going to follow the arrow for taro t. We're going to see it's a function, it's boba, and it's going to be this function in here, right? Because it says its parent f1. Right, so now we're going to go into that function. We're opening a frame for it, f2, and its parent is f1. I'm just copying it over from here, and then I'm going to have to give its arguments. So we see that ice gets assigned to 50, right, because I'm passing in here. And then I'm just returning shop ice over 50. So I know that whatever I get from f3 is going to be passed here. I'm going to divide that by 50 after. Cool. So now shop ice. So now I'm going to be passing in ice to the sugar argument here. Right. So, and the reason why I skipped a step here. So since I need to look for shop ice, right, I need to know what function that is. So I'm going to look in my current frame of f2 and say, do I have a variable shop? And I don't. So now I have to go up to my parent frame, which is f1, and look for the shop variable. And I see the shop variable here, and it's this function here, right? So I know that I'm going to be calling this function of boba in the global frame. So now I'm going to be calling this function. So I know that sugar is going to be assigned to 50, because that's what I'm passing here, and ice is equal to 50 right here, right? So I'm going to do sugar here, and then I'm going to return sugar times 5, which is 250. So I see that I have this arrow here, so I'm going to take that out. 250 divided by 50, which is the original return statement, in this boba function, which becomes 5, right? And so I know that whatever f2 returns is going to be returned to price, but I didn't draw the arrow earlier. But this will be just assigned to 5. Cool. And do please erase the arrow so it's easier for us to grade in the future. But yep, this is how this environment diagram should look. Cool. So now for number 3, we're going to be doing Fibonacci sequence. So we see here we're defined some function fib, which is going to give us the nth item of the Fibonacci sequence, right? And we see that here there are 2 recursive calls. So this is definitely some tree recursion going on. And so we're asked to find how many recursive calls to fib we're going to get when we call fib 6. So why don't we draw this out? So I know I'm going to have this fib 6 here, right? And then whenever I have the 6, I'm not going to be returning until I get to fib 2 or less. So that's like kind of like when I'd be stopping, right? But so I'm at fib 6, so I'm definitely not going to stop. So I'm going to be calling fib n-1, which is just 5, and then fib n-2, which is 4. right? And then each of these, so I'm actually just going to go down one side of this tree first. We'll just focus on one side first. So on focus on one side, I know that vibe is not fib 2 or less, so I'm going to go to fib 4 and fib 3. Still not there yet, so we're going to keep going. So fib 3, this is fib 2. Right, so this one I know I can stop. And this one, I'm going to keep it going. So just keep going. So fib 3 gets to fib 2 and fib 1. So we're both stopping here. So I see that here I can count the number I have for fib 3, which is 2. 2 more fib calls, right? And then I can also count the number I have for fib 4, because fib 4 is just 2 calls plus 1 call, right? So I can see that fib 3 here is going to have the same number of recursive calls. This is also going to be 2. This is going to be 3 plus 4. So I guess like we should count itself. So this is 3, kind of 1, 2, 3. This is 1. And so fib 4 was a total of 5 if you include itself. And then fib 3 has a total of 3. I miswrote that. And then fib 5 is just going to be a sum of 5, 3, and itself. So it's 9. Right? So we also see that there's this fib 4 over here. And we already have calculated value for that. So that's just 5. So now we can just add the two together, which is because it's 9 plus 5 is 14, plus 1 for fib 6 itself, and we get a solution of 15. But you can also draw this out too if you want. This is going to be like fib 2, fib 1. This is a really big tree too, so it's like fib 3, fib 2, fib 1, and this is fib 2, right? So now I can just also just count them all up. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So this is what our full tree is, but there's easier ways to like kind of like reduce the number of drawing and number of counting you have to do. But yeah, cool. So now we're going to be doing number 4, which is a shard number. So basically, we're just going to be checking if a number is equal to the sum of its digits. So why don't we get started with the problem? So we see here that in this line immediately, I know that I'm going to have to summing, or I'm going to have to be doing some kind of iteration. And it's probably going to be some while loop. I'll write it down tentatively for now because I just don't see a way that like there's a list that I can use a for loop with. There's some iterator that I can be using a for loop with. So if I'm thinking that I'm going to have to use a while loop now. Next, I see a sum digits kind of variable name here. So I feel like the way to do this problem is probably going to be adding, just like summing up all the digits and then comparing against the original number at the very end. So why don't I just like implement kind of sum digits first. So sum digits, I know I'm gonna have to be keeping track of some like base number, right? And I don't exactly know what temp is gonna be used for right now, so I'll just leave that blank. But I'm gonna be kind of doing some while loop until something is. So I know that like I'm gonna be doing until n. At least I'll just use n. I'll just keep like 4 dividing n is greater than 0. I'm going to be doing sum digits is equal to n mod 10 plus sum digits. So I'm just adding the last kind of like the last value in it, and then temp. So I see that temp here seems to be like the thing that I want to be keeping track of, kind of how many times I want to iterate, because that's the one. I'm not modifying n inside this while loop, so I'm probably going to be doing until temp is greater than 0, and this is probably going to use n. And so I'm going to do temp 4 divided by 10. Right, so this is just a standard kind of summing the digits from homework. We've done it a couple times, or similar concepts to this, where we're just kind of adding the ones value, kind of shaving it off, and then getting a new ones value the next time we're in a while loop. So yeah, in the end we can just return n is equal to some digits, right? Because this in the end, after we're done with our while loop, should be the sum of all the digits we have, and then n we haven't touched yet, so it's still the original number, and we're just comparing the two and getting a Boolean out of it. Cool. So now for number 5, we're going to be doing NBA players. So essentially we're kind of given that this is how players look like, and this is how it's like the NBA kind of data structure of like a bunch of players looks like. So we see that here we want to do team filters. So we kind of want to make a function that sees if that player is on a certain team, and we kind of decide if they're on a certain team with what it seems like is a higher order function. Because if we look here, we're kind of saying team filter is going to return a function, and that function kind of checks if it's a warrior, or depending on whatever team we put here. Right? So I know that at the bottom I'm going to be returning some higher order function. So maybe I call it like team check or something. And this is going to take in a player, right? Because we want to, if you look here, we're doing like NBA 0. So this is going to be this LeBron James player. And we're kind of checking if that person is on the Warriors. And so really, so we're going to be returning this team check function. And all we're going to be doing in team check, really it looks like all we have to make sure is this player's, to return a Boolean, right? So we're going to try to check that the player's team, which we can access by doing this, right, is that's equal to whatever got passed in originally as team. So yeah, that's all we have to do for this problem. For the next few, this one we're going to take in a list of players and return a list of players on that team. So cool. So now we're kind of like filtering, right? So this seems like it's a good place to use filter, some of the built-in functions here, right? So probably we can actually take advantage of team filter too. Right, so we can filter. And since we're getting passed in a team here, we can pass that team into a called team filter, and then we get back this function that checks if each person's like a given player's on a team, right? So if we do team filter team, right, now we'll be able to check for whatever team we want to check for or get a list of. We can it'll get passed into here, and we'll return this new team check function that checks if it's on that given team, right? And then we can just give it our list we want to subset. Right? And you can also do this with like a list comprehension, and that probably seems like it would work too. I'm pretty sure we accepted those kind of answers too. And cool. So for the next problem, doing get player height. So for this one, we're just given a player and we want to return the height. Seems pretty straightforward because I can always just grab their height here from this tuple, from the player tuple, right? So it seems like I can just return the player 1, right? That's it. And then cool, for this last one, team average. So we're allowed to use things from before to find the average height of the players on that team. Okay, cool. So I guess the first thing we probably want to do is kind of get all the players on the team. So I think this would be a good place to use this teammates function. So let's just grab the team first. So team's already taken, so let's call it cur team equals teammates players team. So now this cur team should be a list of kind of all the players on a given team, and then once I get that, I want to get all their heights, right? So now I want to be able to get, like, kind of apply get player height to all of them. So I can either use like map, or I can do it like a list comprehension. Either way works, but let's just call a new list heights, and we're just going to be doing kind of map get player height on current team. And then once we have the heights, we have this list of all the heights of those people on that team, right? We can simply just kind of find the average of it. So we're going to be getting we're summing all the heights together, right? So sum heights, then we're going to be dividing out how many players there are. So that's just going to be the length of heights, because each player has their own height. So cool, that's it for problem 5. Cool, so now on to the last problem of the test. So in this problem, we're kind of looking at this game where there's like some given amount of cookies, and I can take up to 3, and I want to see if I can guarantee, if there's any possibility of me guaranteeing a win, which is like, I'm the last person to take the last cookie, right? Okay, cool, yeah, so from here, I can see we probably want to do it some recursively, right? So I want to be thinking about some base case and some recursive case, right? So at least for my base case, I'll probably just write down a temporary one right now, and we'll see, because I can see that this thing here probably is giving me a hint at the base case. So less than or equal to 0, maybe. Well, it seems like we'll return false, which kind of makes sense, right? Because if we're at 0 or if we're at -1, we didn't take the last cookie. That means the other person took the last cookie, and so we probably can't guarantee a win that way, right? So that's, for now, it seems like it makes sense for a base case, right? So now I have to kind of think about what my recursive case would be. So essentially, this might be a tree recursion problem, right? Because I might just kind of recurse through every single possible amount of cookies I can take. So if anybody remembers count change, kind of recursing through every single possibility, or at each layer of recursion, I'm either taking the coin or I don't. And in the same sense, at every layer of recursion, I can take up to 3 cookies, or 1, 2, or 3 cookies. So we can kind of draw it out. So if I have n cookies to start, right, the next kind of recursive cases at least would be, right, they could be this one, I have n minus 2 cookies, and then n minus 3, right? And the reason why I'm drawing these different shapes is because let's say this layer was me, right? We're just starting out the game. I'm given a number in n, right? And in this next layer, this is my opponent, so this is my friend, right? And so if I know that if my friend can win in one of these, then I know that I can't. If my friend can guarantee a win from here, then I can't guarantee a win going down that path, right? But if I can guarantee that my friend won't win in one of these, then I can guarantee that I have a path to guarantee my win instead, right? So for right now, we'll just kind of maybe do a for loop. I'll do cookies, and just to be able to iterate through and kind of make the 3 different recursive calls that I'm going to need. So I'm going to use this for loop to do that. And this cookies variable is kind of how many cookies am I going to take for in a given recursive call, right? So the really important thing here is to remember that I kind of want the opposite of what my friend can do, and because my friend's going to call more, right, 3 more, and these are going to be me again. So I'm still going to be using the same function, right? But this is kind of where the recursive leap of faith comes in, right? So if I can guarantee a win from here, right? Or sorry, if my friend can guarantee a win from here, if can win of n minus 1 is true, if this is true, then I know I can't guarantee a win going down this path. And if all of these become true and this one's true, then I know that this is false for me, right? Because my friend is going to be able to guarantee a win from all three of these positions. So that's kind of like what we don't want, right? So what we do want is to see if there's any possibility. So my friend has to be like can. So I'm going to abbreviate can win to CW. So can win n minus 1 and can win n minus 2 and can win n minus 3. So if all these three are true, then it's false for me, right? But in my case, if any of these are false, if any of these are false, so it's like if can win n minus 1 or can win n minus 2, or so like if any of these are false, right, then that I know that that's true for me. So I'm kind of like this is my friend looking at it. So if all of these three are true, then my friend guarantees a win. But if I negate it, if I negate all of these, then I know that's kind of what I get, right? Because if any of these are false, then I know that I have a path to the very end, right? So in our case, we kind of want to be negating the recursive call, right? If not, can. Right, so this is checking if my friend can win if I take like one cookie, right? And if they can win if I take one cookie, then I want to go check if they can win if I get 2 cookies. And if again can win is true, then I want to be like, oh, then maybe I'll try 3 cookies. And if I try 3 cookies, but if 3 cookies is still true, then ultimately I want to return false, right? So after I've tried all of these, after I like go through everything in my for loop, and I like realize I can't win, then I'm gonna have to return false, right? But if any of these are true, or if any of these are false, so if my friend at any of these positions can't win, then I know that I can win, right? And this also works. This logic is kind of a leap of faith because I kind of have to like believe that like at every layer it's going to work. So once I go down a layer, right, my friend's also going to be calling this. So it's going to be kind of like not can win like n minus like 2, something like that, right? And if that's true and this is true, then I know this one's true. So it's kind of like a big leap of faith to kind of like understand like this, how this negating works, right? Because every other because with this not, then every other kind of recursive call becomes like, or a recursive layer, I guess, it becomes to represent me and not my friend. Okay. So there's also another way to do this problem. So if you were clever and during a test situation you came up with this problem, we gave you full credit for it. But if you realize that if number starts at a multiple of 4, it guarantees that you can't win ever. And then if it's any other number, like that's not a multiple of 4, then you always can win. So it's just a couple line solution there, if you could have thought of it during the test. But yeah, this is the recursive solution, at least that we were looking for. But yeah, we gave credit to either one. So if you came up with the other clever way to do it, then it's totally fine too. So yep, this is the end of the midterm walkthrough, and hopefully this helped show you how to like maybe approach and kind of think about some of the problems that might be on the midterm in the future.